Hello guys, welcome back to my YouTube channel. Today I'm going to be going over some conventional mechanisms, walking you through the step-by-step process of how I would go through a question, such as the ones that I'm going to present. For example, when you react an alkene, where an alkene would be when two carbons that are attached to one another, they don't just have a sigma bond, they actually have a pi bond. So the pi bond is going to be the second bond between carbons. This is arbitrary, carbons 1 and carbon 2. First things first, we want to highlight all electrons that could potentially be involved in the mechanism. So these are going to be pi electrons and our lone pairs. So there's 2 electrons in each bond because, well, what's a bond made up of? A bond is made up of the sharing of electrons between 2 atoms, where each atom contributes 1 electron. So hence, between these 2 carbons in this pi bond, there's 2 electrons, but each carbon, a part of the pi bond, is contributing 1. So then we have HBr. Draw out all your bonds. H bond to Br. Br is going to have 3 sets of lone pairs. And then this bond between the H and the Br, there's going to be 2 electrons in it. H is going to be delta plus. Well, because the bromine is pulling electrons towards itself, because it's electronegative, it's a thief of electrons. Therefore, the H is very delta plus. Hence, it's attackable by nucleophilic things. So what's nucleophilic? Well, anything such as pi electrons or lone pairs, if the atom has a negative charge, per se. But here we got this pi bond. There's 2 carbons, carbon 1, carbon 2. So let's say these 2 electrons flick up, and they shoot out and they go attack this H. 2 in, because we're attacking with 2 electrons. 2 up and out. What do you get? If they attack from C1, let's do that in example number 1. This new H, we could say it's green, is going to be attached to C1. And we're going to do the opposite situation right after this. So now in the initial structure, C1 had 2 H's. And C2 had 1 H. Because each carbon needs 4 bonds. Well, after C1 flicks out and grabs this new H, well, it still has 4 bonds. But carbon 2, it now has a deficit of electrons because it lost that 1 electron contributing in the pi bond. So it is positively charged. But what happened to the bromine? Well, the bromine still has those 3 sets of lone pairs, but it also has the lone pair that was initially 2 electrons in a bond between hydrogen and the bromine, and it is negatively charged. So now, opposites attract. So what happens? Well, this bromine can go 2 in and attack this carbon that was in a deficit. So you get a bromine at carbon number 2, and you get a hydrogen at carbon number 1. Bada bing, bada boom. So what happened in the opposite situation? So let's say, this double bond, and this double bond decided to attack for, say, from carbon number 2. 2 in, 2 out, same kind of trend. But now the hydrogen, let's label it in pink, ended up at carbon number 2. So what if the hydrogen ended up there? This is a what-if situation. Well, now that would mean that carbon 1 would be left in that deficit. So now, let's compare the 2 intermediate forms. So this would be intermediate form number 1, and this would be intermediate form number 2. What carbocation is more stable? We have this structure, and in option number 2, we have this structure. Which carbocation is more stable? Well, this comes down to, well, how many alkyl groups are surrounding the carbocation? This carbon is 2'. Why? Well, because there's 2 areas of alkyl donation. And alkyl groups, CH3 groups, are electron donors. And if you're in a deficit of electrons, hence you're cationic, electron donors are very useful to you because they're bringing you back to neutrality. This is a good thing. Whereas this guy is only 1'. It only has 1 area of alkyl donation. So in example number 2, the carbocation is much less stable than the carbocation in example number 1 because it only has 1 area of alkyl donation helping it out. You could think of this as a charity. The positive charges are a charity. And if you're a charity and you have 1 huge donor, let's say Elon Musk is donating to your charity, that's pretty awesome, right? But you have a second charity where it has 6 different types of Elon Musk that are all donating to your charity. What charity has more funding? Well, the one with more donating groups. This guy would have more donating groups. In comparison to this guy. Therefore, this guy is more rich. Rich in what? Well, rich in electrons and organic chemistry, but it's really the same thing if you put it into perspective of a real life situation. So then from here, well, similar thing would happen. The Br minus would go 2 in, and then your product would be a bromine there, and the initial hydrogen that was grabbed by C2 would be here. So these are the two potential products, but this guy is the better option. Why? Because it went through a more stable carbocation intermediate, because it was a 2' carbocation versus a 1' carbocation, which is better in terms of stability. This mechanism in example number 2 can also proceed, but you're going to need peroxides. But that's a story for a different day. Hopefully this makes sense. And have a good day. Let me know if you have any questions, and make sure to leave a like, comment, and save or subscribe to my channel. Have a good day.